Good morning everyone. We are here to give a seminar on efficient sign digit to CSD recording circuits. Recording essentially means converting from one form to the another form. I am Pavan Kumar and my teammates are Shivam and Vasishta. So sign digit is one form of number representation where we use the digit set -1, 0 and 1 in order to represent any number. As you can see, the number 15 is represented in three different ways, which essentially says that the sign digit representation is not unique and has more number of non-zero digits. Having more number of non-zero digits while representing any number makes the computation of makes multiplication difficult. So we need a number representation which has minimal number of non-zero digits and has unique representation for each number. CSD is one such representation, and in order to represent any digit we need at least 2 bits, 1 bit to represent the sign and another bit to represent the magnitude of that digit. -1 is represented as 1 1, +1 is represented as 0 1, 0 is represented as 0 0. And coming to the reason why we have chosen this paper is this paper it aims to solve the complexity and the inefficiency associated with the traditional recording circuits. In traditional recording circuits, in order to convert any number from SD to CSD, the number is first converted from SD to 2's complement and 2's complement to CSD. Having 2's complement is as the intermediate step, it requires binary subtractor. So this paper aims to eliminate the use of this binary subtractor and convert directly from SD to CSD. By doing this, we improve the speed of the recording circuit. So here we have implemented two such implementations, one with using parallel prefix structure which further improves the speed of the circuit, and one without using parallel prefix structure. So there is this algorithm where we convert an n-bit number into an n+1 CSD output. This circuit has the delay of order O of n. In order to further improve this delay, we use parallel prefix structures, and Shivam will continue from here.
So as Pavan has already explained the circuit without parallel prefix, we can notice one thing over there. This yi, the output, and the carry, the next carry, not only depending on xi and xi plus 1, but it also depend on the previous carry. So we can resemble this circuit with a ripple carry adder, which will calculate its previous carry before calculating the next carry. So for calculating the final output, we need to calculate all the carries beforehand. So it will, as Pavan said, it will take order of n time complexity. And in this paper, we are proposing this new circuit which is using parallel prefix. So this circuit has three stages. First is, as we can see, pre-processing, parallel prefix tree, and post-processing. In pre-processing, we are giving all our 9 bits, like all our n bits, which we are representing in 0 0 0 1 and 1 1 kind of. So in pre-processing block, it will generate two signals, one with the sign of each carry, which is parallelly we are calculating sign of all the carries, and the other one is carry signal, which is generate, propagate, and anti-propagate. Here we can notice one thing, that in the previous case, here we can notice one thing, that sign of Ci are not depending on previous carries. They are just depending on the previous values of input and their sign, which we are providing parallelly. So we can calculate sign of all carries parallelly at once. Now coming back to the magnitude of Ci, pre-processing will generate, as we can see in the block, pre-processing will generate three signals: generate, propagate, and anti-propagate. Uh, we can calculate three carry signals by equations as shown in the slides. अरे यार, वो कहाँ है? Sorry. Yeah, we can use these three equations to calculate carry propagation and anti-propagation to generate all these three equations. And here also we can notice that all these signals are dependent on magnitude of xi plus 1 and magnitude of xi and that of sine of ci, which we have already calculated. Now the carry signal will be given into our PPT block, which will further calculate the magnitude of CI parallelly. Now Vasishta will tell that how this PPT block is going to act, and this is the code which we have implemented to calculate GI, PI, and AI, and also we have calculated this absolute value of x, sine of CI, and sine of xi. वो समाचार मत पढ़ना पड़ेगा भाई.
Yeah, now I am going to explain the next module, which is PPT, which means parallel prefix tree. As Shivam has explained, we have calculated up to now is the carry signals of each and every digit. Now we are going to calculate the carry chains from lower digit to each and every digit, which can be represented by G of I comma j, P of I comma j, and A of I comma j. Uh, yeah. See, these are the elements in PPT: J of I comma j, P of I comma j, A of I comma j. Now, in this equation J of I comma j, it is depending upon J of I comma k plus 1, where k is ranging from jth bit to I minus 1th bit. So we can use any value of k. So now in this code I am using k is equal to j. So from that equation J of I comma j is depending upon J of I comma j plus 1 and J of j comma j, and similarly p and anti-propagate also. So now why we are calculating this carry, these are called carry chains from jth bit to ith bit. So we are calculating these carry chains to get the value of magnitude of carry output in CSD. So yeah, now I will explain little bit about this equation, how to calculate. J of I comma j is depending upon J of I comma j plus 1. So to calculate J of I comma j plus 1, we need again J of I comma j plus 2, and J of I comma j plus 2 is depending upon again J of I comma j plus 3. So like that j is increasing, so it will go up to J of I comma I. So J of I comma I is the carry signal from the pre-processing block, as Shivam has explained. So final conclusion is, to calculate J of I comma j, we need J of I minus 1 comma I minus 1, J of I minus 2 comma I minus 2. So up to J of z comma up to J of 0 comma 0. From that we can calculate these carry chains of all generate, propagate, and anti-propagate. So now the next module is implementation of this each and every block. Now in this implementation I am using lowercase characters. So this is gate level implementation. So in pre-processing block we have calculated carry signals of carry signals. So these are the equations to implement these carry signals. So G of I comma I is, as you see, it is only depending upon magnitude of xi plus 1 and magnitude of xi, and which is nothing but it is equal to J of I comma I and A of I comma I. So similarly these carry signals are calculated in this implementation of pre-processing block. So these are the Verilog codes for implementing those. And yeah, yeah, and now the gate level implementations of that PPT structure, those I have explained for previous PPT structure. The similar explanation will go here. So this implementation includes the recursive process again. These are the Verilog codes for that, and now the magnitude of carry is depending upon j of I minus 1 comma 0. So that is the main reason we need that PPT which have all carry signals. Now we can easily calculate this j of I minus 1 comma 0 and similarly p of I minus 1 comma 0. So, and the final block is post processing. In that we are implementing the sign of output and the magnitude of output. So yeah, there are equations to implement those. So these are the Verilog modules to implement those equations, and we have taken this output into the FPGA, and we can show the output through LEDs of FPGA, and these are the simulation results for some random inputs. And yeah, as you can see here, in FPGA there are sliding switches and LEDs. So we are giving inputs through sliding switches, and there are 16 sliding switches. So, and since the input is in sign digit representation, we can't give that input directly. So each sign digit is converting to 2-bit binary, and we are giving those inputs here through sliding switches. So by default the MSB should be 0 for all these calculations. So 0 means in binary it is 2-bit 00. So this last 2 digits I am directly giving as 00. So we have remaining 14 sliding switches. So we can give maximum 7-bit SD input. So we can get output as 7-bit output of magnitude and sign of that output as 7-bit. So here we have given some random example: 1 bar 1 bar 1 1 bar 1 1 bar 1. So this 1 bar is 1 1 1 1 is 0 1. So like that we have given input through sliding switches, and these first 7 LEDs are representing the magnitude, and these last 7 LEDs are representing the sign of output. So similarly, yeah, this is one example how we have implemented this video. Okay, yeah.
0 0, the input 0 0 1
So
1
as you can see, this is the random input I am taking and giving as input through sliding switches.
1 1
result. So
here
here
is
is
the
the
And this is the manual calculation of output.
using for
1 0.
Here we have got exactly.
Yeah.